Okay, so let's just pick up where we left off. You can see that our answer involved natural logarithms. This is going to be the case for most problems involving partial fractions. So let's just continue right into another example. Let's start with a pair of fractions this time. Okay, so I'm going to write since 1 over x plus 1 plus 1 over x minus 2 can be rewritten. I'm going to do this relatively quickly. I'm just going to put a common denominator of x plus 1 times x minus 2. The first fraction would have been missing a factor of x minus 2. The second fraction would have been missing a factor of x plus 1. So when we combine them over one denominator, we'll get that sum. That equals 2x minus 1 all over x squared minus x minus 2. Okay, so since this is true, if I had been given the problem, find the integral of 2x minus 1 over x squared minus x minus 2 with respect to x, we could rewrite that as the integral of 1 over x plus 1 integrated with respect to x plus the integral of 1 over x minus 2 integrated with respect to x, right? And from what we had just seen in the previous video, I think we saw the first one already. This will simply be ln of x plus 1 with absolute values plus the natural log of the absolute value of x minus 2 plus a constant. All right, if we do use substitution, the key is for the second one, we would let u equal x minus 2. So du still equals dx, so we don't get any other constants in there. We're going to see later on when u is a little more complicated, we have to be a little bit more careful when we take the antiderivative, but this is what we get for this. Now remember, we can apply rules of logarithms. So this will condense down to ln of the absolute value of x plus 1 times x minus 2 plus c, which will reduce to the natural log of, we can take the product of those, x squared minus x minus 2 when we FOIL it, plus c. Okay, so you can see that's just the denominator of what we had above, all right? Now let's convince ourselves that this is right by using another method, all right? It turns out this would have been a lovely u substitution problem. What we want to show quickly is that we actually get the same answer whichever way we do it. So when you look at this and you say, should I use u substitution or partial fractions? The answer is use whichever one occurs to you first. Neither method is too easy, although u substitution is probably faster if you don't recognize what the fractions would be. So if we let u equal x squared minus x minus 2, du dx is 2x minus 1, which is the numerator. So if we were to let du equal 2x minus 1 dx, that's the numerator of what we're integrating. So we can call all of that du, and we can call the denominator u. So we just end up with the integral, if we put all of this together, of du over u, which just remember that's the same as you're going to see when you have a 1 over u du or a 1 over x dx. It often gets, mathematicians sort of like to write it this way. So you're often going to see that. So a du in the numerator is the same as putting with respect to u at the end. So the result of this is that we should have ln of the absolute value of u plus c. And since u is x squared minus x minus 2, we can put that in and see that we get exactly the same answer. And I think it's pretty easy to argue that when u substitution will work, it's usually the easiest method. But this does show that by breaking the integral into fractions, we are able to also get the answer. Now, where we're going to go in the next video is how do you take something that's complicated, like the integrand that we just worked with, when you haven't been given the fractions? How do we find out what the fractions are? So it's, once you know what the fractions are, it's pretty easy to integrate because we keep getting natural logs as antiderivatives. But figuring out what the fractions are is a little algebraic trick. And so we want to review that trick in the next video.